This presentation is going to cover both inclined plane and wedge. To start off with the inclined plane, it is a flat surface set at an angle or an incline that has no moving parts. We've all seen those. You either push objects up it or you pull objects down it, depending on what you need to do. In this picture, I have an inclined plane where I am pushing a cart up a ramp over the course of 15 feet. Pushing it up the ramp 15 feet allows me to raise the cart a total of 4 feet. Getting back to everything else that we've talked about, if I'm dealing with distances, I'm looking for an ideal mechanical advantage. The formula for ideal mechanical Here's the formula for ideal mechanical advantage. The length or the slope of the ramp over the height. This is still going to be our distance of effort, not resistance, over our distance of resistance. Same formula we've been using for all the other types of simple machines. In the case of this simple machine, my length is my 15 feet. My height is the 4 feet. If I divide those out, I get an ideal mechanical advantage of 3.75. To look at our actual mechanical advantage, I'm going to start by looking at this ramp. I am putting in 20 pounds of effort to move a 50-pound resistance. Our actual mechanical advantage formula has not changed. Force of resistance over my force of effort. I plug my values in. My actual mechanical advantage is 2.5. And as with all the other simple machines, I can find out what the efficiency is by taking my actual mechanical advantage and putting it over my ideal mechanical advantage and then dividing or multiplying by 100. Once I do that, I find that this system is 67% efficient. The next topic to come across is our wedge. It is yet another simple machine. It functions as a moving inclined plane. So that you also know, it tapers to a thin edge and it's used for splitting, raising heavy bodies, or for tightening by being driven into something. You typically see these as axes to split wood. Here's a very simple drawing of what a wedge looks like. These arrows here show my force of resistance. This arrow here shows my force of effort. Something to note for future slides. Here you can see what our ideal mechanical advantage is with a wedge. We're talking about our length perpendicular to the height, this side here, and then our height, which is here at the top. This is the same as what we had said before, as this being our distance of our effort and our distance of our resistance. In the case of this problem, for me to find my ideal mechanical advantage, all I need to do is apply and substitute my dE over my dr. We know that dr is going to be the height, and my dE is the length. So now all I have to do is divide. And when I divide, I get 3.3. Now that we've done the ideal mechanical advantage of a wedge, there's only one thing left to do, the actual mechanical advantage of a wedge. My wedge actual mechanical advantage formula is the same formula I've used for every other simple machine. We have our actual mechanical advantage being equal to my force of resistance over my force of effort. As I said at the beginning of the wedge section, this is going to be my force of resistance, and this is going to be my force of effort. So I'm going to just fill them in. 700 pounds over 250 pounds. That gives me 2.8. Now that I have my actual mechanical advantage, I want to find out what the efficiency is. That formula, as it has been every other time we've used it, is AMA over IMA, and then multiplying that by 100. So to substitute, I have 2.8 over 3.33, and I'm going to multiply that by 100, which gives me an 84% efficiency. That's the fifth of our 6 simple machines. The last one is a screw, which we will cover here very soon.